Our next speaker, also associated with Jack's team, as a matter of fact, he's the deputy PI for Jack's Lunar team, is Joe Lazio, and he will be speaking from JPL. His talk is Probing the Dark Ages and Cosmic Dawn, a Roadmap for NASA Astrophysics. So Joe, take it away.
Oh, can you hear me now?
Yeah, gotcha.
Okay, good. Let me start with just a bit of context. NASA Astrophysics, the division within the Science Mission Directorate, is currently in the midst of what they are calling a road mapping exercise. This is an exercise in which NASA Astrophysics is attempting to come up with the set of next flagship missions, and actually not even missions so much as compelling scientific investigations for the next 30 years. And this presentation was one of the ones that was presented, actually invited to make a presentation before that committee. We've heard many times that Cosmic Dawn is one of the top 3 science priorities. From the perspective of this community, from the perspective of the lunar and planetary science community, one of the interesting things about this topic is that it leads naturally to, in some sense, a synthesis between astrophysics and planetary science, or that there are now suddenly common destinations. In general, astronomers are starting to look very favorably on free space because it is a largely clean environment. But there are specific science investigations, such as the one about which you've heard much already this morning, that actually drive you to planet, or in this case, a satellite surface. And as a result, there's the possibility of synthesis between astrophysics and planetary science. Thus, it's a compelling science identified in the most recent Astronomy Decadal Survey. I believe that this picture has already been shown, but just to remind you that we are focused on the hydrogen atom, and it's also interesting from the standpoint, or it's one of those nice aspects. We're actually talking now about radiation that has a human scale. The wavelength is 21 centimeters, which is something of that size. Due to the universal redshift, it is redshifted, or the wavelength increases to actually human scales of a couple of meters. This picture's already been shown as well, but the idea behind this science investigation that we are believing that NASA Astrophysics should adopt over the next 20 to 30 years is that there is a rich variety of both cosmology and astrophysics to be probed by using this 21 centimeter line. And in fact, there are actually 3 different epochs that one can identify. And they are the Dark Ages, which is truly the Dark Ages in the universe before there was any starlight. There was first light, which I believe is also sometimes mixed up with cosmic dawn, but it's essentially the effect of the first stars forming. And then finally, EOR, or epoch of reionization, which is when actually galaxies form, and the universe makes a transition to what is today a largely ionized state. This is perhaps difficult, or it's not intuitive for neutral human beings to understand or to appreciate, but most of the universe is in fact ionized, not neutral like ourselves. And just to understand this, if you think about the solar system, about 99% of the mass in the solar system is in the sun, and the sun is a largely ionized body. Thus, there are these 3 different epochs corresponding to different processes or astrophysical events occurring in the universe. This 21 centimeter line is generated, or a signal is generated at each epoch, and there are different amplitudes of signals occurring at different redshifts or at different frequencies that tell us different information about the universe and particularly about its evolution. Again, the measurement technique that we are proposing is that there's the cosmic microwave background. This is, of course, the remnant glow, if you will, from the Big Bang itself. And if there is hydrogen gas between the cosmic microwave background and a receptor that we have, then this 21 centimeter line can be excited or can be produced either in absorption or in emission, and there's the appropriate very complex looking equation at the bottom of the screen. This is there to illustrate that there are actually a variety of different effects that lead into the amplitude. And depending upon which effect is most important or which aspect is most important in the evolution of the universe, one can then infer from a measured brightness temperature, the T sub B, what the characteristics of the universe are. So for instance, the first factor that you see there is the neutral fraction, so how much of the universe is actually neutral in neutral hydrogen versus in an ionized state is one of the things that one can hope to infer, and in fact we've just heard some discussion on that point. I'm going to focus specifically on the measurements that are required from space, or from which we will require space-based observations, because that's the realm of NASA. In the dark ages, the expectation is that the gas, the neutral gas, the hydrogen, will cool faster than the photon gas, which is namely the cosmic microwave background. So this 21 centimeter line will appear in absorption. And in fact, this is a very simple physics problem. Essentially, as you heard, there are really only two things going on. You've got expanding, cooling gases. And I've certainly had theorist colleagues who have said, this curve has to look like this. And if it doesn't, there's something very fundamental about cosmology that we do not understand. That's at redshifts of, as you see there in the graph, something like 100. Those are down at frequencies of, say, 10 to 30 megahertz. That's at frequencies at which the ionosphere is significant, and it certainly requires going to space. The next effect, or the next epoch, is this first light when the stars are turning on, and we've already heard a bit of discussion about that, and what is the balance between the UV field created by the first stars and the X-ray heating likely created by the first accreting black holes. One of the important points to emphasize about this plot is that there are a range of possible amplitudes that this signal could occupy, and in fact, theoretical predictions are that the range and amplitudes could vary by as much as a factor of 2 or more. So I'm showing one particular realization, but it could be substantially different than that, depending upon when the first stars kick in, how strong the first X-rays are. So both of these, the dark ages and first light, are really almost entirely unconstrained. Well, they're not entirely unconstrained, but there are significant uncertainties in the shape of this plot. This is now a recap of that signal, and from the NASA astrophysics standpoint, they have two programs. One is, actually they have three, but two are of relevance here. Cosmic Origins, which is sort of how did we get here, and that is clearly in the realm of when did the first stars form. They also have a program, Physics of the Cosmos, which is trying to understand the extremes of physical laws. A part of that is cosmology, and that's where the dark ages come into play. So this is not only something that possibly marries or has aspects for which planetary science could share commonalities, but it's also something that crosses programmatic boundaries within NASA astrophysics itself. Finally, if I can get the movie to run here, one of the other things, we've been showing pictures often of the global signature. Much of the power, and in fact some of the Nobel Prize for the studies of the cosmic microwave background come from the top plot, which is the Planck view of the cosmic microwave background, and that shows the variations, the fluctuations across the sky from the cosmic microwave background. Well, we expect fluctuations in the 21 centimeter signal as well, fluctuations in space, but also in time as the universe evolves. And this is one of the critical differences between the cosmic microwave background and the 21 centimeter signal, in that if we can form the equivalent power spectrum of the 21 centimeter fluctuations, we can actually watch that evolve, whereas the cosmic microwave background is a snapshot in time. It occurs at a particular epoch at a redshift of 1100 when the universe first becomes transparent. And that's all the look that you get at the universe from the cosmic microwave background. Whereas if we can exploit the 21 centimeter signal, we now have a way to essentially watch the universe evolve. Thus, there are two different technical implementations. One is a sky average spectrum, which requires a relatively low angular resolution instrument. And there's a H1 fluctuation spectrum approach, which requires a very high angular resolution instrument. People have talked about the ionosphere. This movie is simply a movie of the sky actually taken from the ground now, but it illustrates an important aspect of why we need to go to space. The three bright sources there are the three brightest celestial radio sources in the sky. What you're actually seeing is a movie, and every so often you'll see these very bright flashes of light. These bright flashes of light are reflections of distant TV transmitter off meteor trails as meteors vaporize in the Earth's upper atmosphere. So this kind of observation from the ground is getting hit by two simultaneous effects. One, the Earth has an atmosphere. It has an ionosphere that can reflect and modify the signals, on top of the fact that all of this electronic equipment that we use and love produces signals that are much, much stronger than the celestial signals we're trying to detect. I'll skip over the radio spectrum other than to emphasize that the amount that's actually utilized from the ground, or is actually in some sense reserved from the ground for radio astronomy use, is very small. And importantly, from the radio spectrum standpoint, the far side of the moon, and actually the volume behind the far side of the moon, is internationally recognized as a potential preserve for radio astronomy. In the context of this NASA Astrophysics exercise, they had asked for identifying way stations, things that would happen along the course of, say, the next 30 years. And I attempt to identify, over the course of 10 years, the first way station would be to measure when first light occurs, and that would be something like a lunar orbiter, perhaps, say, the DARE mission that we've heard about. 20 years out, the objective would be to actually go after the H1 fluctuation spectrum, which would require angular resolution and would almost certainly require an array on the far side of the moon. And 30 years out, looking very far out, it's actually to get into the dark ages. I will be agnostic about whether that is going to be done solely as a sky average measurement or actually as an array. But I think this is it's both challenging and scientifically exciting roadmap. I will skip over some of that, and there are a host of technical challenges. We've heard about some of them. Some of them are things that are actually coupled with technology advancements we'd like in other areas. Just as an example, we'd like to deploy an array on the far side of the moon, which almost certainly would require robotic rovers. Those also have uses within planetary science, as the Mars Curiosity rover is demonstrating. There are other areas where astrophysics clearly has to lead. The kind of antennas and receiver systems that are necessary are simply not going to be developed by anybody else. So I think I will leave it. This is my final slide. I'll leave it there and take questions.
Thanks, Joe. Yeah, great. Well, I don't see any questions in chat, so I will ask one. You mentioned requiring angular resolution at the 20-year point here on your last slide. How much? You know, what kind of angular resolution are we talking about, and what does that translate to in terms of the size of the array?
It would require, say, arc-minute or arc-minute-ish angular resolution, which, if I'm remembering correctly, is sort of comparable to the kind of angular resolution that a person with 20/20 vision has, although at a much different wavelength. And therefore, the angular extent of the spatial extent of the array would have to be at least a few kilometers in scale. Although, because it's being implemented as an interferometer, that doesn't mean you have to deploy something that is a few kilometers in scale. You just have to be able to access sort of few kilometer scale sizes on the far side of the moon to deploy these individual antennas.
Have there been any studies at all to cost something like that out? I know, of course, you guys through Jack's team are developing the technologies to do that, but is there even a ROM kind of a guess at what such a thing would cost?
We did conduct a so-called Astrophysics Strategic Concept Mission Study a few years ago that was actually funded by NASA Astrophysics. And at the time, we did not get anything better than a ROM, but it's certainly a flagship class mission.
Okay, all right. Well, and certainly the kind of technologies that you folks are developing with rovers, putting out the Kapton material and everything are going to reduce the costs, I'm sure. So
yeah, that is certainly the intent. Yes.
yeah, yeah. Well, I hope very much to at least live to see that happen. So thanks very much. Great talk. Really, really, really good stuff. Our next